Well, welcome back. This is now lecture or presentation number 2 in a series on the Collatz Conjecture. We've broken the Collatz Conjecture into several chapters. We started with an introduction. That was the first part. This is the second part that's going to cover several theorems pertaining to the tree for the Collatz Conjecture. And then following this, we'll have a map of the integers, odd integers in P onto the signed integers in the Z set, and the presentation on the spiral representation of the Collatz conjecture. So we'll talk about 7 theorems that are the first steps in the proof of the Collatz conjecture. So theorem 1 is that every odd integer in the tree for the reverse simplified Collatz conjecture can appear only once. We prove this by contradiction. If the same integer n appears in 2 different places in the tree, then it must have 2 different odd number descendants, m1 and m2. And so m1 would be 3n plus 1 over 2 to the I, and m2 would be 3n plus 1 over 2 to the j for different exponents I and j. A little bit of algebra. We just show that m1 times 2 to the I would be 3n plus 1, and that would also be m2 times 2 to the j. This can only happen if the integer 3n plus 1 has 2 different prime factorizations with different exponents for 2. This violates the prime factorization theorem of arithmetic, so therefore that cannot be true. So therefore the 2 values of n, or the 2 descendants of m, cannot exist. So therefore the hypothesis is contradicted and the theorem must be true. Corollary to theorem number 1 is that the tree cannot have any loops that connect to the root at n equal 1. This is depicted in the short diagram down below, where n descends through 2 separate branches through m1 and m2, and those then combine to reach back to the root node at n equal 1. Such a loop in the tree would require 2 descendants from at least one of the nodes. In this case, it would be node n. Since theorem 1 says there cannot be 2 separate descendants, a loop of this type cannot exist. So the corollary must be true. This brings us to theorem 2, that the tree for the reverse simplified Collatz conjecture has only a single root at n equal 1. So again, we prove this by applying the descendant equation to determine the descendant of a node m equal to 3n plus 1 over 2 to the k. We set n equal to m, and we get n is equal to 3n plus 1 over 2 to the k, or by simplifying here, 1 is equal to n times 2 to the k minus 3. So this means that n, or the number 1, can only have factors of 1, so therefore n must be 1 and 2 to the k minus 3 must be 1, or in other words, n is 1 and k is equal to 2. So there's only one root in the tree. Theorem 3 is that the root node 1 has no descendants. Again, we apply the descendant equation to the root node 1. The descendant would be m equal to 3n plus 1 over 2 to the j. N equal 1, so that's 4 over 2 to the j, so j is equal to 2. So therefore, the root node 1 is the only descendant. The corollary to 3.1 is that any ascending node branching from the root node 1 cannot be in a loop, since those nodes have only a single path down to the root, and the path must stop at the root. So if we look at theorems 1, 2, and 3, and the corollaries, the implication of all this is that any odd integer in the reverse simplified Collatz conjecture tree either has descendants that end at the root n equal 1, or the descendants continue to increase indefinitely, off to infinity. If all the odd integers descend to the root, then the reverse simplified Collatz conjecture must be true, and then so is the simplified Collatz conjecture, and so is the ordinary Collatz conjecture. So basically the proof that follows from here is that we show that odd integers inevitably descend to smaller odd integers, and this therefore has to converge down to the root at n equal 1. This brings us to Theorem 4, that the nodes ni that are multiples of 3, i.e. equal to 0 mod 3, are terminating nodes with no ascending branches. Here we apply the ascending equation P1 to the node ni to get ni plus 1 is equal to ni times 2 to the k minus 1 over 3 for some integer k, such that ni times 2 to the k minus 1 is divisible by 3. We put in 3j in there for ni. We get 3j times 2 to the k minus 3, or minus 1 divided by 3, which is j times 2 to the k. That's a multiple of 3 minus 1/3, which is not an integer. So therefore, the equation does not have an integer solution, and therefore there's no ascending values from the starting node 3j. So therefore the theorem must be true. Corollaries to Theorem 4 are Corollary 4.1 and 4.2. Corollary 4.1 is that nodes that are multiples of 3 can only descend to a node with residue 1 or 5 mod 6, which are the other odd integers besides multiples of 3. And Corollary 4.2 is that we may exclude multiples of 3 from O and apply the equations for the reverse simplified Collatz conjecture to the set P, where P is the set of odd integers that have residues 1 or 5 modulo 6. The tree for the set P may then be mapped later into the signed integers in the set Z. We'll see to that in step 3. Theorem 5 is that there are no loops in the reverse simplified Collatz conjecture tree except the trivial loop for the root at n equal 1. This proof is a little bit more complex. We define the number of elements in the, or numbers in the loop as lambda. So we've shown here at the bottom a couple of possible loops for lambda equal 1, lambda equal 2, and lambda equal 3. Then we apply the descendant equation lambda times to show that the descendant from ni would be ni minus lambda, and that would equal to 3 to the lambda times ni, plus 3 to the lambda minus 1, plus 3 to the lambda minus 2, and so forth, plus 3 plus 1, all divided by 2 to the k for some exponent k that yields a odd number in the result. We can simplify the sum of the powers of 3 to a sum function called s of lambda, which is equal to 1/2 times 3 to the lambda minus 1. To continue the proof, there are several conditions that have to be satisfied in order to be a valid solution for a possible loop in the tree. First of all, the descendant equation has to be satisfied for n, k, and lambda. And we restate the equation as a Diophantine equation, which would be 2 to the k times n would equal 3 to the lambda times n plus s of lambda. So the solution of that Diophantine equation would have to apply to the elements of the loop. There are lambda elements in the loop, so there have to be lambda different solutions to that equation, or they could all be the same solution, but then you don't have descendants that descend to each other. The only way that happens is if the root node 1 is the descendant. So we see that the only solution that can apply here would be n equal 1, lambda equal 1, and k equal 2. We'll see a little bit more analysis on the next slide why this is so. So again, we restate the descendant equation, 2 to the k times n plus, equal to 3 to the lambda times n plus s of lambda. A couple of properties here. N has to be an odd number in P. The left-hand side is 2 to the k times n, so that's an even number. The right-hand side, 3 to the lambda times n, is an odd number, so that means s of lambda has to be odd in order to balance out to an even number. S of lambda is only odd if lambda is odd, so we can only consider cases where lambda is 1, 3, or 5, or so forth. The factors of S of lambda must also be satisfied, so 2 to the k minus 3 to the lambda must be a factor of S of lambda, and then n would also be a factor of S of lambda. So that means the GCD of 2 to the k minus 3 to the lambda and S of lambda has to be greater than 1. There's also a limit for k that's related to the 3 to the lambda term here. So 3 to the lambda has to be less than k, or 2 to the k, and then in turn has to be less than 3 to the lambda plus S of lambda over n for some value of n. By substituting value or the formula for S of lambda and putting in some sort of a minimum value for n, we get a fairly tight constraint on lambda and k, and in particular the log to the base 2 of 3 is going to equal be slightly less than k over lambda, and then log of base 2 plus 3 plus the log of this other complex expression as a function of n and lambda has to be greater than k over lambda. Basically, k over lambda is a very tight approximation to the log to the base 2 of 3, which would be 1.585 and so forth. We can make this constraint tighter and tighter by using larger values for n as a minimum value for the possible loop numbers. We'll see that if we set n equal 1, that the first numbers that satisfy the constraint, aside from lambda equal 1, are lambda equal 27, lambda equal 39, lambda equal 45, and lambda equal 49. These 4 values are easy to check, and we see that they don't lead to any loops in the tree. So that lets us increase the value of n to a larger value. In fact, by exhaustive search, we can verify that there aren't any loops for values of n under 1,000. So we go to the next odd number above 1,000, which is 1,001. If we apply that in the equation, then we get a very tight limit that suggests that the next solution would be lambda equal 10,281. We can verify that also fails the GCD condition, because 2 to the k minus 3 to the lambda is not a factor of S of lambda. So that lets us set an even tighter value, an even higher value for the minimum value of n and so forth. And if you repeat this process, what you discover is that there's basically no value of k and lambda and S of lambda and n that's computable that satisfies this equation, aside from the trivial solution at the root node n equal 1. This brings us to theorem number 6. Nodes ni that have a residue 1 mod 4 descend to a smaller node value in a single iteration. This is easily shown. We just set ni equal to 4j plus 1 for some integer j. We apply that to the descendant equation, 3n plus 1 over 2 to the k, to get 12j plus 4 over 2 to the k. So we set k equal to 2, and that reduces then to 3j plus 1, and we see that 3j plus 1 is less than the starting value of 4j plus 1, so therefore the theorem must be true. Theorem 7 is an iteration on this. We show that integers that have residue 3 mod 16 descend to a smaller node value in 2 steps. So we set ni equal to 16j plus 3. We apply that to the descendant equation twice, and a little bit of algebra there, and you get the descendant is 9j plus 2, which is less than 16j plus 3, so therefore this theorem must be true. So theorem 6 basically says that half of the integers in P descend to a smaller odd integer in a single step. Theorem 7 shows that 1/8 of the integers in P descend to a smaller odd integer in 2 steps. Combining with theorem 6 and 7 together, you get 5/8 of the odd integers descend in 1 or 2 steps to a smaller integer, and 3/8 of the odd integers take more than 2 steps. We can continue this method for larger moduli and more residues, but the algebra, of course, gets correspondingly more complex, and it's simply easier to do numerical calculations by testing different integers modulo various moduli, and develop the table that's on the next slide that we call the fraction of odd numbers. And we observe here that if all the odd integers descend to smaller odd integers in some number of steps, then the reverse simplified Collatz conjecture must be true, and therefore so is a simplified Collatz conjecture in the standard Collatz conjecture. To do this, we'll define a decrement length, which is how many iterations you have to do in order to get to a smaller node value. So for example here, for starting value 17, a single decrement gets you to, or a single step in the descendant sequence gets you to 13. So the decrement length would be 1. If we take a different starting value of 7, then that would have a decrement length of 4, because it takes 4 iterations to get to 5, and 5 is less than 7. So if we do the computer calculations to find out how many residues decrement after some number in the decrement length, we get a table like this. So for example, we've already seen that for decrement length 1 in modulus 4, there's 1 residue. For decrement length 2 in modulus 16, there's 1 residue. For decrement length 3 in modulus 32, there's 2 residues that are 11 and 23. For decrement length 4, modulus 128, there are 3 residues that are 7, 15, and 59, and so forth. We can continue this all the way down to 12, decrement length 12, and modulus there, is 1,048,576. There's 2,652 residues, starting with residue 239. Each of these leads to a fraction of the odd numbers in P. So the first one has a fraction that's a half. The next one is 1/8. For decrement length 3, that's also 1/8. For decrement length 4, we're talking about 3 over 128. And 3 over 64, and so forth. We can accumulate them in the cum column there, so that's 0.5, then 0.625, then 0.75. So that tells us what fraction of the integers in P are going to go to or descend to a smaller integer after some number of steps in the decrement length. And then 1 minus the cum in the last column there tells us what fraction of the numbers in P take more than that number of steps to reach a decrement. And you can see that cumulative fraction progressively decreases. So these are just some notes on the fraction table. The main point here is that the residues in the residue column are a sequence that's documented in the OEIS. It's sequence A100982, and if you look at that, that is an easily iterated sequence that lets us extrapolate this series on out indefinitely. If we extrapolate it out for decrement lengths out to 100, and then look at the cumulative, complementary cumulative probability, we see it decreases rather strongly out there at lengths of 100. Here, if we plot it on a semi-log scale, we see it converges to an asymptotic slope that decreases at the rate of one octave for every 10 decrements. So this lets us easily predict the fraction of numbers in P that are going to require more iterations, for very large decrement lengths. The conclusion from this table is that we can make the number of, or the fraction in p that takes longer to decrement as small as we want, simply by increasing the number of the decrement lengths. So this says that as the tree grows, the probability that it's always going to descend to a smaller value in the tree is basically inevitably true. It converges to unity, and so therefore at least from a computable point of view, the reverse simplified Collatz conjecture must be true. So that concludes this section of the presentations. Thank you, and I'll see you in the next.